states around here, but we should try to disentangle this entire manifold here, because this manifold is actually manifold created by the pz orbitals of the carbon. So if we want to create Wannier functions, say for the case of graphene or for a carbon nanotube, we shouldn't stop neither in a metal nor a semiconductor just at the Fermi energy or just at the occupied manifold, because there has been a lot of hybridization between the top of the valence and the bottom of the conduction. And instead what we want to extract is the black, the blue, and the red, because the black is really the bonding combination of sp2 orbitals, and the blue and the red are all the pz orbitals, and the black here are the anti-bonding combination. You see the symmetry. Bonding combination of sp2, anti-bonding combination of sp2, and the manifold of all the pz. So if you do first a disentanglement, we separate, say we take everything below the green line, and in this window we separate the red from the black, and then we localize, we now have more orbitals, because now we have one orbital per covalent bond, exactly as before, but now we have also one orbital per carbon bond instead of one orbital every two carbon bonds. But you see, these look very well behaved pz orbitals that are just asymmetric because of curvature. This is the nanotube, so this is the inside of the nanotube, and this is the outside of the nanotube. And if you look at the band structure interpolation, you'll see it will look perfect. I'll show it in a moment, but just to remind you what we have done. We have started from block orbitals, and we have disentangled and localized, and we have obtained Wannier functions. Once we have Wannier functions, we can interpolate back through block sums. This is really, the block sum or the linear combination of atomic orbitals, and get a wave function at any arbitrary k point. So we started with a coarse sampling in the Brillouin zone, your usual Moncost-Pack meshes that you do in the calculation. We have obtained Wannier function. From the Wannier function, we can obtain wave function back at any k point. We never do this explicitly, but if we want to calculate a matrix element of the Hamiltonian, what we have is that actually only very few terms will be left, again, because here you have a sum over the block sum of all the Wannier function, each one translated by a lattice vector. Same here, and only Wannier functions that are nearby will have a non-negligible matrix element. So most of the matrix elements in this infinite block sum here and the infinite block sum here are 0, and by the definition of the principal layers, only the matrix element between Wannier functions that sit in the same principal layer or nearby principal layers are there. And so to calculate the band structure of the carbon nanotube from this Wannier function is extremely inexpensive. And now, because sorry, let me go for a moment to the next slide. And now, because we have properly taken into account the fact that there was a lot of mixing between the upper and the lower pi manifold, we get a perfect description of everything that we care about. You see, the electronic structure code would give you the red points, and the Wannier interpolation gives you the solid lines, with sort of perfect agreement everywhere, and completely missing every state above this value that are of the anti-bonding kind. And that's because sort of our basis set is extremely limited. To do the PWSCF calculation, the red points, we used thousands and thousands of plane wave basis sets. While to do the Wannier interpolation, we are diagonalizing onto a basis that is just 2.5 Wannier functions per every carbon atom. So every 2 carbon atoms, there are only 5 Wannier functions. So this is really the smallest possible basis set in existence that on top gives you a perfect band structure. That's why they are so good to construct the electronic structure of nanostructures. And if I go back, this was the example I wanted to describe. suppose that we look at this 5,5 carbon nanotube. So the band structure that you would have, this is 1/2 of the Brillouin zone, and so this red line is what is calculated, say, by PWSCF. So now suppose that we construct Wannier functions out of these bands, again, sort of disentangling the upper manifold and taking everything below the Fermi energy. As you know, we are going to do a discretization of the Brillouin zone, that is, we calculate eigenstates only at certain k points. And so I'm going to take a sort of k-point measure that has 5 points, so this, and this, and this, and this, and this. So I'm doing a coarse discretization of the Brillouin zone, and so in actually this discretization, the system doesn't look like a metal at all, because it really is equivalent, once I fold the Brillouin zone, at taking all these points here. So the system, if I look at it, looks with my discretization like an insulator with a huge gap of 2 electron volts, because this is what my electronic structure code knows. It knows only states at that sort of k-point mesh of 5 k-point, and those 5 k-point in this Brillouin zone, once you fold them, are equivalent to the points sitting here at the gamma point. I do disentanglement, I do localization, and I do Wannier interpolation, and what I obtain when I do Wannier interpolation are these solid black lines here that you see reproduce perfectly well the metallic character. You see when you unfold them, they overlap exactly with the PWSCF calculation, and if I calculate, say, the conductance of the density of states from the green function, they sort of find perfectly a metallic system, and they even find, the right Van Hove singularities in the density of states and the conductance for points that had nothing to do with anything I sampled, because I only sampled this wave function here and this wave function here. So it's the Wannier interpolation that is actually able to recover all the band structure in between and recover the right curvature and the local Van Hove singularity. So not only we can use Wannier functions to construct, say, the electronic structure of large-scale system, but we can use them as very accurate interpolators, not only of the energy, but of any operator. Because, what I just described before had to do with, being able to calculate, say, the Hamiltonian, but you could put any operator. Sorry, this is an operator, and this is a 0, so we are calculating the Hamiltonian matrix, the operator matrix in the Wannier basis, and once we have this object that is very short range, because these things are localized, we can Fourier transform it and get it at every k point in space, and by diagonalizing it, we get whatever eigenvalues we want with very inexpensive operation. And I have here from Jonathan Yates and Ivo Sousa some examples in which Wannier interpolation is used. Well, this is sort of first looking at a case of a metal that we have already studied, and look at the comparison between the interpolated Wannier functions in blue, and the interpolated band structure in blue and the exact band structure in red. And if we look at the Wannier functions obtained from coarse mesh, as we increase the fineness of the mesh, we see the error in describing the band structure is exponentially decreasing. So as we make our k-point mesh finer and finer, we do a better and better and better description of our system with exponential accuracy. And this becomes very relevant if you have very complex systems whose physical properties depends only, say, on states in a very narrow region. Suppose that you want to calculate properties like the night shifts, or the orbital magnetization, or the NMR, or the anomalous Hall effect, or electron-phonon coupling, a lot of times those are quantities that are not depending on all the states in the Brillouin zone, but only those very close to the Fermi surface. So in a way, it's instead of relying on an integral in 3 dimensions, you have to just take an integral in 2 dimensions. But in order to do that accurate, you need an enormous mesh if you want to do things accurate, and you might want to use efficient interpolators. And this is a case, I won't go into the detail of this, in which Jonathan and Ivo were calculating the anomalous Hall effect. I'll describe it graphically, in which you want to calculate properties like the Berry curvature around the Fermi energy, and this is a value of the different bands and their contribution to the Fermi curvature. And actually, in this case, there are sort of different sort of formulation of the problem, but you see that in a lot of cases, bands do not contribute, and then there are sort of little pockets where there are huge contribution. And so if you want to do these integrals accurately, either you use really enormous K-point meshes over the Brillouin zone, and you explicitly diagonalize with your electronic structure code the problem everywhere, or you use an interpolation. Because again, you see this is just an enlargement of that zone. You see how delicate these integrals are. There are sort of places where the bands do not matter at all, and places where there are huge contributions. And so the calculation of the anomalous Hall effect was done a few years ago using, it's not written here, but using millions of K-points, so an extremely expensive calculation. And Jonathan and Ivo were able to replace that just by doing an 8 by 8 by 8 calculation from first principle, and then doing a straightforward Wannier interpolation and calculating all those Berry connection and Berry phases that go into the anomalous Hall effect, and getting very carefully converged results. That, by the way, doesn't really match with experiment, but that's a different issue. At least there is a consistency here. And just to conclude, to go back to our transport properties, we were, able to calculate transport properties in this system, and actually discovered that the probability of an electron to go through this functionalized region was actually decaying very, very rapidly with the number of molecules. So we are studying a system that has, something like 3,000 atoms in the central region, and then is semi-infinite, something that if you wanted to do from first principle would be absolutely impossible. We do it with these building blocks, and we look at what is the probability of transmission that for the perfect nanotube would be in certain units of conductance 2, and we discover that very, very soon it goes down to 0 as you increase the number of molecules. Even 30 molecules here are able to completely destroy the conductance. Basically because when you attach a molecule, here you transform the carbon atom from sp2 bonded with 3 covalent bonds to sp3 with 4 covalent bonds, and that's a very strong scattering centers. And I showed these results at IBM, and sort of the next year they actually did the experiment on the same system, in which they took a nanotube, they functionalized it with the same sort of RL ligand, and what they found was sort of very low conductance, very high resistivity for the functionalized metallic tube, and as soon as it was heated and these residues were leaving the system, you would still be metallic, but with a conductance that was 5 orders of magnitude larger. And so this idea of localized Wannier functions can be used to sort of, really deal with the structure of very large scale systems. And, with regard to the question that we had before, how does it work for a metal? Well, the carbon nanotube is a metal, and if we look at the matrix element of the Hamiltonian between these pz orbitals, we see that in a semi-logarithmic scale, they go down with an exponential decay. So sufficient to truncate very early these matrix elements in the Hamiltonian to get a very good representation of the band structure. And actually, you see, no matter where you cut, you can cut as close as here, and you get a perfect representation of the band structure. And this can be used to study a wealth of problems in which you want to get to the large-scale system by studying the electronic structure of a small system and then building up things. And I won't go into the details of this, but say we are using it for things like, say, an infinite strand of DNA, where you capture the electronic structure of small fragments, and then you build it up for the entire system. And I think with this, and this is work that we are doing with Arash, I conclude the presentation. Let's see if there are any questions, and then in the afternoon, Nicola Marzari will be in charge of the tutorial. Thanks a lot. Any question before lunch? Please.
So if we could erase your memory of all the work you did on the Wannier functions and ask you right now what would be the, what would you think make the best type binding basis? How would you answer the question?
So it's exactly as you imagine. So it's atomic like basis of sp3 or sp3 plus d orbitals. There are sort of cases like the carbon nanotube, in which you see very clearly that the bonding combination of the sp2, that is the covalent bond plus the pz, is exactly what you need. But if you were a sort of enlightened chemist or physicist, you would have told me beforehand that that is what makes chemical sense. And so, if anything, the work that we have done is just to give you the right numbers for what your intuition would give you. There are sort of more exotic cases, like in the case of copper, say, that I showed you before, you can actually get a fantastic representation of the first 7 bands by using 5D Wannier functions, as everyone would expect, that are sitting on the copper atom. And then you can have 2 S-like Wannier functions that sit in the interstitials. And that's really a sort of accidental issue that comes from the fact that the really good basis would be 9, 5 d orbitals plus 4 sp3. But it turns out that the way the sp3 work is that there is this very interesting sort of superposition and resonance of the sp3 pointing towards the interstitial that actually gives you sort of S-like Wannier functions in the interstitial. But of course they are not physical, because as soon as you sort of distort copper, that resonance disappears. So if you wanted to have a tight binding Hamiltonian that you can really use for ab initio molecular dynamics, you really want atomic-like orbitals. So in many ways, we haven't discovered anything. It's just we have a tool to make the tight binding Hamiltonian from first principles, especially in cases where you have chemistry going on, like in the case of the chemical functionalization. So it's sort of easy to derive empirically a decent tight binding Hamiltonian, say for a homogeneous system, just for carbon in the sp3 state. But if you want to do carbon, functionalized with a benzene ring and so on, putting numbers there becomes more arbitrary. And so this is just first principle in that. Please.
See the class of examples that you have given, starting from the chemical activities of molecules to the polarization, then to transport. It seems that if the Wannier function becomes a very good representation of system, irrespective of their structure and size, so a time would come when people only rely on Wannier function, start from there doing any calculation, because you have already shown that there are certain cases in which computer time becomes very important, those which are now in access of supercomputer and so on. So they can do this kind of problem.
Yeah, so that's a very good point. Now, let's take the case that you have just seen. Suppose we take diamond, so carbon in sp3 configuration. So we would have the perfect Wannier functions to do What happens when you take diamond and you take a surface of diamond and you warm it up? If you go to 2000 Celsius, it exfoliates graphitic layers. So what you have is really, you start from sp3 diamond and you end up with sp2 diamond. I can give you very good Wannier function for sp3 diamond. I can give you very good Wannier function for sp2 diamond. But if you want to describe the entire process, you need to describe something that is sp3, that has sp3, has sp2, and probably something else. And we haven't even started to look at that problem. And I do believe that these techniques could actually be used very effectively to obtain, say, the optimal sort of basis set that is minimal and very accurate. But we haven't gotten to the stage in being able to use those for sort of arbitrary cases. But it's really the inverse of the quantum chemistry approach. I mean, the quantum chemistry approach is sort of trying with localized bases that you make better and better. Here we start from the perfect basis set that is a complete basis set, plane waves with a high cutoff, and we figure out what is the localized basis that works. And so we plan to use that, but it takes time.
I'm actually thinking in that sense. So in future, within say 5 years, if you can create a bank, sp2, sp3, anything in between, so people will just use that bank.
No, that's exactly what one of the things we would like to do. Yeah. Lunchtime, huh? Okay. See you later. We'll start at 2 o'clock and finish early because there is Matthias at 5 and then there is the barbecue. Okay? 2 o'clock, and remember the evaluation.